So basically, in my part, 8 weeks before midterm exam, it's all about deriving equations in Appendix B, right? And it's like a fundamental for transport phenomena, which will be applied in any types of transport phenomena problems. And also after midterm, as you all know, that you're going to learn how to do the simulation, okay? In this case, it will be the CFD, computational fluid dynamics. So even if using the CFD, it's pretty, I mean, it's easier, right? Because you just select all the features in the program and then you just hit run and then it will calculate everything for you. But the main key thing is how do you know that what you're computing from the simulation is correct? Like the answer that you get from the simulation is correct. So that's why it's very important to understand the fundamental of this equation so that you know how to apply and select the right equations in the simulations. Okay, because for example, if your system is dealing with compressible fluid, for example, okay, but in your program in the CFD, you apply the Navier-Stokes equation to solve your system. So of course, the answer that you get from the simulation will not be realistic or even correct, right? Because you apply the wrong equation for solving for solving the equations for your system. So that's why you need to understand all the fundamentals of the transport phenomena equations. Okay, because I think some of you might be wondering why we have to understand or learn about deriving the equations. It's just like a complicated things, right? And yeah, that's why I want you to understand and know each equation can be used for specific reasons. Okay. All right. So today we're going to go through practice actually the exercises about the momentum transport. All right. Just like we did for the mass transport. Okay, we're going to start with the basic exercise that you might have seen in the problems when you were in the undergraduate program. If those of you who have taken transport phenomena in your undergraduate program before, okay? So this will be a different approach. Like I said, that in your undergraduate program, you have applied the shell balance approach, right? But in this case, we are going to use the conservation equation form of equation. Okay, so it will be different. So in this case, you don't need to do the shell thing, which sometimes is more complicated. All right. So if I have a pipe, okay, this is a basic and general exercise that you have seen before. So if I have a flow through pipe, okay, I have a flow through pipe. Of course, a pipe is in a cylindrical shape. So at the top of the, this is a part of the pipe, okay, from C naught to ZL, okay, and the pressure is P naught to PL as well, all right, and the radius for the pipe is a big R, okay. So first we're going to define our system, right? So of course, the system for this one will be this whole pipe, right? This whole pipe. So what kind of coordinate you're going to use for this problem? Cylindrical, obviously. Okay. So let's make a list of the assumption. In this case, we have a flow of fluid through this pipe from top to the bottom, okay? And we're going to find out the velocity profile of the fluid in the pipe, okay? So let's make a list of the assumption. The assumption would be, of course, steady state, okay? And then anything else? incompressible fluid, of course, because in this case, it doesn't specify what type of fluid that is flowing through this pipe, right? It can be compressible fluid or incompressible fluid. So if you are going to use the, if you doesn't, if you don't specify that it's an incompressible fluid at the beginning, it means that when you apply the equation of motion, okay, you have to use this equation in B5 equations, which is right here, equation of motion, in terms of shear stress, tau, right? And you can see here that, for example, in Cartesian, okay, you see that the on the right-hand side term, it will be in the form of shear stress, right? But if you can make an assumption that the fluid is incompressible fluid and Newtonian fluid, that means that you can instead use the equations in B6, which is the Navier-Stokes equation, all right? So B6 is the equation of motion for Newtonian fluid with constant rho and mu, which is the Navier-Stokes equation. So you can see on the right-hand side, instead of the shear stress, it will be in the form of velocity now, which will be easier to use, okay? So that's why we would want to assume that the liquid in this system is incompressible fluid and Newtonian fluid, all right? It has to be both, okay? Incompressible and Newtonian fluid. Please make a note in your lecture, okay, that in this case, the mu and rho will be constant, all right? It has to be both, all right? And then I will have another assumption, which is the no slip condition. You still remember, right? It's the condition where it occurs on the interface between the fluid and the solid, okay? The velocity of the fluid will be equal to the velocity of the solid, okay? And then smooth pipe. All right, so how do we start for this one? We're going to start this exercise, which is the basic one, and it's in cylindrical coordinates. So of course, we're going to apply this equation from Appendix B, which is B6, okay? So in this case, we're going to use the cylindrical coordinates, okay, in this one. So let's take a look. In this one, we will have R, theta, and Z, right? So let's define the direction for each axis. So this will be in R, this will be in Z, okay? So do you think from taking a look at this equation, you see that we will have a lot of velocity, okay, in each directions. We are going to have VR, V theta, and VZ, right, in the equation. Let's take a look if we have all these three velocities. Do we have VR in this system? No. Why? Because the fluid is flowing down only, right? So it's not flowing radially. So in this case, we won't have VR. Do we have V theta? Does it go like in circle? No, okay. Do we have VZ? Yes, of course it's flowing down, okay. And if you take a look at these equations again, okay. If you take a look at this equation, you see that VZ, okay, actually in all velocity, VZ will be in a function of R, theta, and Z, right? Like you can see that we have VZ by dr, VZ by d theta, VZ by dc, okay? So do you think it's a function of R, theta, or Z? Do you think VZ is a function of R? What does it mean by VZ when you're considering if VZ is a function of R? It means that if you choose at different r's, okay, you still have the same vz, same velocity. Like if you have if you're focusing on at the middle of the pipe, you will have one vz, right? But if you move further at different r, do you still have the vz? Okay, if it's the same, vc is the same, that means that vc is not a function of r. But if vc varies with r, it means that it's a function of r, right? So does vc is a function of r? Yes or no? No. Why? So when you say no, it means that VC is all constant along R direction. Okay. Does anyone think yes? Yes. Okay. Why? Okay, that's very good because of the no slip condition. All right. So if you remember that the hold on, that the velocity profile, if let's say is a laminar flow, the velocity in the middle of the pipe will be the highest, right? And the velocity that is close to the wall of the pipe will be 0 according to no slip condition. And if you remember, it's like a parabolic shape, right? Where it's something like this. Still remember? And even if it's the turbulent flow, is something is also the velocity will vary along r direction as well, but it's not in parabolic shape. Okay, so you can see right here that vz, okay, changes in r direction. That means that vc is a function of r. All right, and the red graph right here, this one, is what we're going to find out. We're going to determine. All right. I'll show you later. So let me remove this. Okay. So we have VC that is a function of R. Next, is VC a function of theta? That means that any angle VC changes? No, right? It's supposed to be uniform. So in this case is no. Is VC a function of Z? So when changing the Z, like you go further down, VC changes. This is quite a tricky one. Huh? It's constant. Okay. So if you say that it's constant means that any z from z0 to zl, the velocity in z direction doesn't change. Okay, so it's not a function of z, because in this case we just this pipe is just like a part of the very long pipe. So if you consider like if we have a very long pipe like this, like from fourth floor to the first floor, for example, okay, it's like 30 meters, for example, okay, and there is a water flowing down, okay, but the picture right here on the left hand side that I'm showing you, it's just like a part of the long pipe, okay, right here, which is this one, okay. What I'm saying is that it's just a very short length, okay, of the long pipe, okay. That means that velocity will not be changed, okay. Velocity will be roughly constant, but if you consider a whole length of pipe, okay, instead of cutting into small pieces, but if you consider the whole long pipe right here, the velocity will be changed along z direction. I mean, it will be it will receive the effect of the gravity now. Okay, so of course the velocity will be even higher and higher when it's flowing down further. Okay, so that means that the velocity at the bottom right here will be faster compared to the velocity at the top. Okay, but in this problem, you can actually make another assumption right here that it's just a part of the long pipe. Okay, so the length of the pipe that we're considering right now is not that long. That doesn't make the velocity in z direction change, okay? But if you consider a whole long pipe like this, of course, the vz will be a function of z, all right? So that will be different, okay? Any questions about this? Okay, all right. So in this case, we will have Vz is a function of R, or you can say that Vz by dr will not be equal to 0, all right? But Vz by d theta and Vc by dz is equal to 0, okay? Any questions about this part? I will make it slow for this part. For those of you who've already taken transport phenomena, I know that this one might be easy for you because you've seen this type of exercise before. But we have several students who are not chemical engineering undergraduated, so we have to go very slowly. All right. Next step. Can you open the file, the appendix B in your own iPad or laptop? Anything? I would like you to work on these equations in cylindrical coordinates. So please consider all this term. Which term can be taken 0? Okay, which term can be taken as 0? Which one can be neglected? Can you do all the finalize everything? Okay, and then let's see what terms that we have left in each direction. Cut off all the terms that are 0. And any terms that you're still deciding if it's 0 or not, just leave it there, okay? All done? Done? Okay, great. I think some of you are still working on it. Are you done? Done? Shan? Yeah? What terms do you have left in each direction? Mhm. G, no, not that. It's not that small. It's not small enough. There will be some case that the G can be neglected. I'll show you maybe if we have time, I will show you. But this is like you cannot neglect the G. Yeah, yeah. Good question. All right, I think you're all done. So let's take a look in our direction first. Is this term 0? Come on, all together. Yes, why? Steady state, good job. Next one. Next one. 0 or not? No, no, why? 0, right? Because, huh? DV, let's go back to here. You can see here that we only have VZ, right? So VR and V theta are all zero. So any terms that have VR, it's going to be all zero, right? VR, so you can go very quick, okay? VR and V theta are equal to zero, so 0, 0, 0. But be careful, okay? Don't go like, oh, they're all zero. All right. So let's go back to the R direction. On the left-hand side is they're all zero, okay? On the right-hand side, dP by dR, does pressure change in R direction? Does pressure change in R direction? In R direction, do you think pressure change? No or yes? If you're not sure, just leave it, okay? Just leave it like that, okay? All right, so I'm going to circle it. All right, what about rho GR? Rho GR. Do we have gravity in R direction? No, right? So just leave it like that. Sorry, just cancel it. All right. So what we have left is just dP by dR equal to 0 for R direction. Okay. Next is the theta direction. Does pressure change in theta direction? In any angle, does pressure change? If you're not sure, just leave it. Okay, just leave it like that. All right. Do we have G theta? Gravity in theta direction? No, right? So just cancel it. So again, what we have is just dP by d theta equal to 0. All right. Last one, in z direction. Let's take a look in each term. Do we have the first term? Is it 0? dVz by dt, is it 0? Yes, 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 because it's steady state, right? Anything that changes in with time. Oop. Hold on. Which one? Okay, so it will be 0. Next one, we have VR equal to 0. V theta equal to 0. What about this term? What about this term? Is it 0? No, Vz is not 0, but what about dVz by dz? 0? Okay, let's go back to here. We have talked about this, right? Vz is not a function of z. That means that dVz by dz is equal to 0, right? So this term is equal to 0, okay? Next, on the right-hand side, dP by dz, does pressure change in z direction? Not sure. Okay, not sure. Okay, not sure, that's good. Leave it, just leave it. But in this case, pressure changes in z direction, okay? Next one, this term. Do we have this term? In your own notes, do you leave it or it's 0? Keep it, right? Why? Because Vz is not, sorry, it's a function of R, all right? So that means it's not equal to 0. So circle it. Okay, next one is 0 and all 0, right? What about last term, rho Gz? Do we have this? Keep it, right? Because it's in a direction of the gravity. All right, so let's make a summary for all the directions. So in R direction, what we have left is the dP by dR equal to 0. Theta is dP by d theta equal to 0. And in Z direction, on the left-hand side is equal to 0. dP by dz plus mu over R. All right. So from here, you can see that in R and in theta direction is it's an equation with P. It's a function of P pressure in a function of r and theta, right? But they're not telling us about in terms of the velocity profile. So we're just going to leave it like that, okay? We're not going to solve it. But what we're going to solve is actually the third equation right here because it's in terms of VZ, okay? So let's rewrite this equation. I'm going to rearrange the equations to dP by dZ and move the gravity to the left-hand side. So it will be rho G, okay? Because G gravity is like a function of Z. It's not a function, but it's the same form, okay? So I will move it on the right-hand side, left-hand side. And on the right-hand side, what you're observing right here is that not only I rearrange the equation, but I also change it from partial derivative to total derivative, okay? So you can see here, dP by dZ is pressure. It means that pressure changes only in Z direction only, but it doesn't change in R or theta, okay? That's why that even if it's a partial derivative, it's also equal to total derivative of pressure changes in Z direction. So it can be changed to total derivative. Same thing with the velocity, okay? You can see that VC is a function of R only, okay? So we can change from partial derivative to total derivative, okay? All right, so in this equation, okay, let me make a square. All right. You can see that on the left-hand side is all a function of Z only, right? It's a function of Z, okay? And on the right-hand side is a function of R, right? How are we going to solve it? This equation. You can see right here that from what we have started at the beginning, right? Make a list of assumptions, defining the system and coordinates, okay? And then apply the Navier-Stokes equation. It's all about transport phenomena thing, right? But apart from this, it's all about maths, okay? It's just like a format when solving the transport phenomena problems. You always start from transport phenomena, and then the rest is all about math, solving the equations, okay? So now we have come to solving the equations, okay? How are you going to solve this one? On the left-hand side is the function of Z, but on the right-hand side is function of R. How are you going to solve it? Yeah, just solve it separately, right? You can see that this is a full or a complete equation where on the left-hand side term is equal to on the right-hand side term. That means that it must be equal to some kind of a constant, some constant, okay? So I'm going to make it equal to C0, okay? That means that on the left-hand side term is equal to C0. Also, the right-hand side term is also equal to 0 because left side term and right-hand side term are equal. So it must be equal to some value. So in this case, I'm going to define it as a C0. Okay. So let's solve it separately. Let's start from the left-hand side first. dP by dZ minus rho G equal to C0. Okay. Can you solve this equation now? Yes, okay, only one. Only one who said yes. Okay, I'm glad. This one is a straightforward to solve, okay? So you just do the integration. This one, only one integration and you're good to go, all right? How are you going to solve this? Integrate it, okay? Can I move to the next page? Are you finished? All right, so do the integrate. You get P equal to rho GZ plus C0 Z plus C1. So integrate the equation, you'll get another constant C1, all right? what would be the next step to solve? Boundary condition, all right? How many boundary conditions do you get? 2, right? That's good. Okay. What will be the first one? So you can see that pressure is a function of Z, right? So you need to find the condition at Z equal to, yeah, just go back to the picture right here, okay? So let me define like this. Can I move this for a second? So in this case, in this picture right here, if you define your coordinates, which is the cylindrical coordinates, right? If you start right here, like where it's at the top of the pipe, this is R, this is Z, okay? So on the Z 0 right here will be equal to 0, right? Z equal to 0 and then Z equal to, let's say L, sorry, to make it simpler. The total L here is the a total length that we're considering, okay, in our system. What would be the pressure? So pressure will be P0 and PL. Is that right? Okay. So substitute these two boundary conditions, okay? You get PL equal to rho GL plus C0L plus P0, okay? Is that right? Substitute this, the second boundary conditions into the equation. So you get Z0 equal to PL P0 L rho G. Is that right? All clear? Yes. YC1. Oh, sorry. Thank you. It's supposed to be C1. Thank you. Thank you. Oh, sorry. You have to solve for C1 first, right? Sorry. Let me move this. Yeah, that's why I'm seeing your face like, oh, what's going on right here? So it will be C1 substitute that, right? Equal to P0. Okay. And then, yeah, this move up right here. Okay. All right. So you start from the first boundary condition, substitute in the equation, okay? What you'll get is the C1 equal to P0, right? And then apply the second boundary condition and solve it again to get C0, right? Okay. Let me show you this just a second before we move on. This is where you define your coordinates, right? At the top of the pipe. But if you do like this direction, RZ, okay? You have to be careful about when you define the coordinates, okay? You can define it anywhere within your system. It can be at the top like this or at the bottom like this, okay? But the direction has to be corresponded to what you define, okay? So in this case, if I define the coordinates at the bottom of the pipe like this, okay? So it means that at Z equal to 0, P will be equal to PL, right? And then Z equal to L. P will be equal to P0. It will switch, okay? And at the end, what you get from your result, the the sign, positive or negative sign, will show anyway, okay, with your velocity profile, all right? So be careful about when defining the coordinates at the beginning. All the direction has to correspond with correspond with the coordinates that you made. But I will give you the trick that you should define the coordinates corresponding to the direction of the flow. Okay, so in this case, the flow is flowing down from top to the bottom, right? So in this case, you might want to set or define your coordinates in z direction going down too, okay, not going up, which is will be the like opposite sign. Okay, it will be easier. If you define like this, it works too, but it will, you'll get confused with the sign. Okay, but yeah, it's better to just follow along the direction of the flow. All right, next one. So we have C0 now. Let me define a little bit more because the equation will be pretty complicated. So let's define P, this one, PI, big P equal to PI minus rho GI. Okay. This is similar to what is in the textbook. Okay. All right. So from this equation right here, we can rewrite it as PL plus rho GL. All right. Is that right? So you just substitute PL with big P plus rho GI right here, okay? Does it make sense? Okay, all right. So I'll move it right here. So I'm not going to the next page. So basically CO will be equal to big PL minus big P0 divided by L. All right. Is that right? Any questions? You're almost done here and then we'll take a break. Done? All right. Let me move to the next page. So on the left-hand side, we're all good, right? We're all good. So let's work on the right-hand side. So the right-hand side will be equal to C0 as well, right? So I will make the right-hand side right here, right-hand side. So is equal to mu over R d dr r d vz by dr is also equal to Z0, okay? Can you solve this equation? Can you solve this equation? It's pretty straightforward, right? Since this is the first exercise for the momentum transport, so I'm going to make a very step-by-step solution, okay? C soon, mu, oh, sorry. All right. So now you can integrate it, okay? So it will be dvz by dr C0 R squared 2 mu. Next exercise, I'm not going to write into details like this anymore, okay? This is all the integration that you're supposed to be able to do on your own. All right. All right. One integrate, another constant coming up. Okay. Do another integration. You get z r squared for mu plus c2 log r c3. All right. Okay. So we're going to solve for C2 and C3 in this case, okay? Two constants. That means we need two boundary conditions, another two boundary conditions. But in this case, it will be velocity z in a function of r, right? What would be the boundary conditions? Two boundary conditions, right? To solve for C2 and C3. At r equal to 0, Vz equal to, what would be Vz where r equal to 0? R equal to 0, it means that it's in the middle of the pipe, right? What would be the velocity in this boundary? Huh? Huh? Uh-huh. Well, if you remember what I just drew the velocity profile, the velocity at in the middle of the pipe should be maximum, right? So there must be some kind of a value. So you could say that it is finite, which is one value, okay? Or you can say that dVz by dr equal to 0. What does it mean by that? So the velocity profile is supposed to look like this, right? Parabolic shape like this, right? So if you take a look at the r equal to 0, which is right here, right? Right here. dVz by dr, meaning that a change of Vz in r direction. So in this case, it will be something like this, like a slope at the r equal to 0. The slope of the velocity profile, the curve, okay, at r equal to 0. So the slope will be equal to 0, all right? So that's why we can either write the boundary condition of dVz by dr equal to 0, okay? Because if you use Vz equal to finite, you won't be able to substitute in this equation because you don't know the value for finite. What would be the maximum velocity at the middle of the pipe, right? Okay, what is the other boundary condition? Big R, right? R equal to big R. Velocity is equal to 0, right? Because of the non-slip condition, no slip condition. Okay. All right. So in this case, how are you going to solve it? Solve for C2 and C3. How are you going to solve it? Please take a look at the first boundary. If you're going to substitute in this equation, you're going to substitute r equal to 0 in this equation, right? So in this term will be equal to 0. Is that right? Next term, C2 log 0. Really? Log 0, how much is it? It's not equal to 1. It's not equal to 0. Yeah, it's like infinite, right? You cannot define it. So if you substitute this boundary into this equation, you won't be able to solve it, all right? And you won't be able to know C2 and C3. So in this case, you might want to just define it where C2 equal to 0 right away so that you can avoid substitute log R equal to log 0. Okay, that's why you just define it where C2 equal to 0 right away. All right. Please make a note yourself. Okay, I'm just going to write like C2 is equal to 0 to avoid having the natural log 0 equal to infinite because it's undefined, all right? And then when you substitute the second boundary condition into the equation, okay, what you get is C3 equal to minus C0 for mu. Can you see at the very bottom? Okay. And since we already have Z0, right? We already have C0. So just substitute it. All right. Almost done here. Hang in there, hang in there. งงไหมคะ? All right, so now we have C0, C2, C3. All right, then put them all back into the equation, okay, which is this one, okay, which is this one. Let me frame it. All right, okay. So substitute C2, C0, C2, and C3 in this equation. So you get Vz equal to PL P0 right? If I take big R square, okay, out of the parenthesis, just rearrange the equation. Okay. Right, right. Rho G go. Oh, it's already no. This is in terms of the big P now. Yeah. So Z right here we have Z0 equal to big PL minus PO divided by L. That's why I'm changing it into this form because otherwise the equation will be longer than this. Yeah. And it's not in the form of rho G anymore, right? Yeah. That is why. Still here? Oh, okay. All right. And if you see this form right here, let's make it practical. Okay, you can see that this is PL minus P0, right? If I go back to the picture again, you see PL minus P0, right? If I go back to the problem right here, do you think the pressure at the top or the bottom is higher? Which one is higher? The pressure at the bottom or the top is higher? At the top? At the top? Really? Actually, the bottom, right? Because it's under the weight of the fluid as well. Okay, but either way, if I rearrange the equation a little bit so that it will be in the form of the general form of the laminar flow for I mean the velocity profile for the laminar flow. Okay, it will be. All right. This is just a rearranging the equation, okay? And if you take a look at this equation, if I substitute the R right here, R right here, if R equal to 0, what does it mean? R equal to 0, it will be in the middle of the pipe, right? In the middle of the pipe, right here, okay? So what you get is the maximum velocity. Is that right? Okay. So from this equation, if I substitute R equal to 0, that means that Vz will be equal to the first term, right? P L R square 4 mu L. Okay. And I would say max right here, maximum. Okay. Or it's just this term actually, because this term will be equal to 0. I mean, equal to 1, right? So I can write it in short that Vz equal to Vmax 1 minus R over R square. All right, that is it for the velocity profile of the flow through pipe in a vertical direction. Okay. So if you substitute R into this equation and calculate for Vz, the velocity profile that you get is actually this one, okay? It's like this one, okay? Any questions about this? All right. This is it's getting late, 10:27 right now, 10:27, right? Yeah, let's take a break for 10 minutes and then we'll come back for a little bit more of this problem and then we'll move on to the next one, okay? More challenging one because this, like I said, this one is a pretty simple and very straightforward. All right, let's meet in 10 minutes. All right, if you remember when we were working on the exercise in mass transport problems, this exercise, you still remember, right? What we got at the end is the concentration profile in terms of the mass fraction, molar fraction, right? So it's the same thing, okay? This is the molar fraction. So besides that, they can also ask you the molar flux, or in this case is the rate of evaporation A into the gas B, okay? So you just apply the big N right here, okay? So at the end, when you solve it, it will be the total molar flux, or it can be the total mass flux as well, okay? Same thing with the momentum transport, okay? For this exercise, they can ask you about the momentum flux, all right? So in this case, if you want to find out the total momentum flux, so momentum flux is actually equal to shear stress, tau, okay? If you remember from last week, week 4, okay, when we derived the equation of motion right here, okay, momentum flux, let me show you. Do we have one? Yeah. We have momentum flux right here, okay, which is equal to all these terms, right? So in this case, we're focusing on the momentum flux of the liquid on the wall of the pipe, okay? So in this case, it will be the shear stress. So in this case, it will be the momentum well, let me start again. When we talk about shear stress, of course, there are total of 9 components, right? Because it is tensor. We have shear RR, R theta, RZ, right? so on. I don't want to write anymore. It's too long. There are a total of 9 components, right? But in any problems, you must consider by yourself which components are not zero, which component is zero, okay? So in this case, do you think which term is non-zero? Tau RR, tau R theta, tau RZ, tau, let me write it anyway. Tau theta theta, tau theta Z, tau RZ, I can hear that. Why? That's a correct answer, by the way. You have to understand the meaning of each component first, right? For example, let's take a look at this one, tau RZ, because Sam just mentioned about it, okay? Tau RZ, what does it mean? When you define this one, do you still remember the meaning of the subscript? I always say that you always start from the right subscript to the left one, right? So this one is basically mean that it's the momentum in Z direction transferring in R direction. Is that right? So it will be different meaning to other components. Okay. So you have to go back to your to the problem itself. Okay. So this one is the flow through pipe. Okay. So a flow through pipe, which direction is the momentum? Momentum is in what direction? Z direction, right? Because momentum is actually mass times velocity. So mass, of course, there is no direction for mass, but the velocity is in Z direction. So of course, the momentum direction will be in Z direction. And which direction does momentum is transferring to? R direction, right? Because velocity is changing in R direction. That means that momentum is changing in R direction accordingly. All right. So out of 9 components right here, we will have, of course, this component tau RZ. What about the rest of the 8 components? Do we have, let's say, tau ZR? Do we have tau ZR? So tau ZR, it means that momentum in R direction, transferring in Z direction, right? Do we have a momentum in R direction? No, right? Because the fluid flow vertically, okay? It doesn't flow radially, okay? So we don't have this term, okay? And if you go through the rest of the each components, that will be equal to 0, okay? So in this case, we will get only one component, which is tau RZ, and it's actually the momentum flux, all right? So momentum flux right here, tau RZ, what will be equal to? If you don't remember, just go to the appendix, okay? Right here. The appendix, it will be in, let's just scroll through. B1, okay? B1. So Newton's law of viscosity, it will be listed, distributed in all coordinates, okay? So the first one is in Cartesian, but in this problem is in cylindrical. So we're going to look at the cylindrical one, all right? So they have listed all components right here, all 9 components, but what we're focusing on is actually tau RZ, this one, right? Can you see it? Tau RZ. So it's actually equal to this term, okay? So you can just look it up on the appendix and apply it in your problem, all right? So in this problem, do we have VR? You still remember? We don't, right? We don't have VR because VR is equal to 0. So just neglect it. And do we have this term dVz by dr? Yes, right? So that will be the term that we're going to find out. So tau will be equal to mu dVz by dr. I again change it into total derivative because Vz is a function of r only. All right, Can you solve this one? Pretty straightforward. Do you know dvz by dr? Rho z. So if you go back to, do we have here? Just go back to your lecture, okay? Let me see. You still have this term, right? If you go back to your notes, okay? You see that you can either differentiate your velocity with respect to r, right? Okay, or if you go back here, you can see that, oh, this term has dvz by dr, right? And you can just substitute C0 and C2 that you already got previously, all right? And then just substitute into that term. That's all right? You following? Okay, you can do either way, okay? So dvz by dr, you can actually differentiate your velocity profile equation that you got, okay, with respect to r. Or if you go back previously, you can see this term right here, okay? You can just substitute r, Z0 and C2, okay, because they are constants, okay? In this case, I'm going to define the boundary condition too, where R equal to big R, which is the area, not the area, it's the location on the wall, okay? So where R equal to big R, okay? So this will be equal to big R as well. All right, so that will be equal to P0 PL R divided by 2L. Okay. Any questions about this? Right, so previously we have a velocity profile that looks something like this, right? Parabolic shape, okay? What would be the momentum flux if you plot it? So if I plot it on the same type right here, okay, where this is, if you consider the shear stress or the momentum flux on the wall, it will be equal to this term, right? But if you consider the shear stress at R equal to 0, how much would it be? Huh? Yes. If I consider the shear stress at the middle of the pipe, how much would it be? It will be equal to 0, okay? Go back and substitute all the terms, okay? It will be equal to 0. So if you plot the momentum flux, okay, what you get is that this is at the middle of the pipe, okay? It will be something like this, where shear RZ equal to 0, and this one is RZ equal to big R, all right? So this is the momentum flux, where you can see that momentum is changing in R direction, okay? Or you can say that this is the direction of the flow of velocity, right? But the transferring direction is in R direction. So it's corresponding being a tensor. Do you still remember tensor? Tensor variable is like it has one magnitude with two directions. So two directions in this case is the one direction for velocity of the flow, and the other one is the transferring direction. All right. besides momentum flux, they can ask you about the force exerted on fluid by the wall. Okay, a force, oh, a force exerted a fluid by the wall. So it's on the wall right here. Okay, how much force would it be in this case? So force is equal to, you know that shear stress is equal to force divided by area, right? Okay, so in this case, force will be shear stress RZ times area. So what would be the area? How RZ, where R equal to big R. What would be the area? The area of the wall, right? Yeah. So it will be equal to 2 pi RL. Is that right? Yeah. The area of the wall in the pipe. Okay. So it's the เส้นรอบวงคูณกับความยาวอะค่ะโอเคไหม The perimeter of the circle times length. All right. So once you have calculate for tau RZ, okay, so you just substitute into this term and times this term. I want this to be in the same page, so I'm going to move this a little bit. So it will be equal to pi r square p minus pl. All right. So this is the force exerted on the by the wall. Force exerted on the fluid by the wall. Okay. You need to specify the condition, boundary condition correctly too, where R equal to big R. All right. All right, good. Any questions about this problem? So since this exercise is pretty new to most of you, I mean, some of you, okay, I will make another modification of this exercise based on this exercise to be your second homework for the today. All right. All right. You'll have the second homework today. I will post it on my course view after this class. All right. The first problem for your homework will be it will be pretty similar to the exercise that we just did. All right. This is problem number 1. Okay, it's just the flow in opposite direction. Previously, we have a flow from top to the bottom, right? But now we're going to flow from the bottom to the top. Okay. Let's go through this together. If it's in this case flowing from the bottom to the top, how are you going to define your coordinates? Where are you going to define your coordinates at? Like this, similar? Or here, 1 or 2? Number 1 or number 2? Number 2 will be easier. I mean, number 1 works too, but since the direction of the flow is opposite to the defined coordinates, right? So it might be easier and better to define the coordinate at the bottom, okay? And you can see that the direction of the flow corresponds to the direction of Z direction as well, okay? All right, that will be, that is your first homework, okay? Second one. Oh. How many homeworks, how many problems do you want? One. Of course. Who would want more? I'll give you 5. All right, now we have a flow through annulus, okay? flow through annulus, it will be a little bit more challenging. Trust me, it's not that complicated. All right. So we have a flow from bottom, flow through annulus, okay? So right here is Z equal to 0, Z equal to L. Yeah, I forgot to define Z equal to 0, Z equal to L. So pressure is the same thing with the first problem that we did together, okay? So this one, the inner pipe, the radius is equal to KR. And the outer pipe, the radius is equal to big R. All right. This one is flow through annulus. ค่ะ big R, big R. Number 3. Number 3. เอาให้จุกๆนะคะสำหรับ flow through pipe หลายๆแบบ All right, last homework, last problem of this homework is that we have and the rod in the middle right here, and the rod is pulling up at the speed of V0. Okay, so you're going to find the flow, the velocity profile of the flow in the annulus. Okay, it's similar to the second one, but the third one is that so the second one, the inner pipe is staying still, right? But the third one is that the inner pipe is pulling up at the velocity V0. All right. So please find what you need to find is that one, velocity profile. Two, momentum flux. 3, force exerted on the wall. Okay, force exerted on fluid by the wall. All right. 3 problems for homework 2. Okay, any questions about any problems? Yeah, a fluid. Yeah, in the annulus. Okay. Yes. It's still in annulus. Yeah, but the rod in the inner pipe here is moving up. Yeah, but this one is fixed. Yeah, this one is pulling up. Yeah, and this is 3 questions, 3 answers that you need to find. If you can draw the profile of the velocity, momentum flux, and also force, that would be nice too. Okay, but it's not required. All right, any questions? I will post this homework on the assignment so that you can submit it directly. Okay, the due date will be next Monday by midnight. Okay, so you've got a whole week, a full week to work on this, right? It's not that hard because you already worked on this, and trust me, it's the same process. But just be careful about the sign going up or going down. That's all. Okay. Everything is all the same. All right. You know when you work on it. All right. All right. Let's move on to the second exercise. Let me draw it first. Okay. It doesn't look good, right? Say die. All right. This exercise is I have a die. Okay. A die is not die, ตาย อะไรอย่างเงี้ยนะ it's like a slot die. When you want to code, a wire. This is actually a wire. You want to coat a wire with some solution. Okay, so the solution is in blue color. So you put it in the die and you slowly pull the wire with the velocity v. Okay, so you can see right here that once you pull this wire like this, the solution will be coated on the surface of the wire. All right. Okay. So we'd like to find an expression for the velocity profile in the annular region of the die. So it will be somewhere around here, okay, where the cross-sectional is tapered, okay? The cross-sectional area will be smaller, all right? So in this case, where is the defined system? Where would you define the system at? You want to establish an expression for the velocity profile in the annular region of the die. So where would it be for system? The die is it's fixed, right? But what you're pulling is actually the wire. So what you're focusing on is right here, okay, where the cross-sectional area is very, very small. So I will make a highlight in, let's use this color so it becomes green now, okay? Can you see that? All right. And what coordinates are you going to use? What coordinates you're going to use? Spherical? No. Cylinder, right? Okay, so this of course will be in R direction, and let's set that this in Z direction. Okay. Do you want to work on this? Maybe I'll let you start working on this problem for a second, and then we'll go through the rest of the solution all together. Okay. Please work on this exercise with your friends. I mean, by yourself and then with your friends. Okay. And then I will walk around. And if you have any questions, just let me know. So be prepared using the equations of Appendix B. Okay. You can use just like the previous exercise. All right. Make a list of assumptions that you need and also start solving the equation right away. B5 or B6. You can apply any equations, all right? Let's start this all together first, and then so you can move on. So since we start with the cylindrical coordinates, we're going to have VR, V theta, and VZ, right? Do we have VR? No, right? Because it's moving towards the right-hand side. So this one is 0. Do we have V theta? No. All right. So we have only VZ, obviously. And VZ is a function of R, theta, or Z. It's a function of R, theta, or Z. R, obviously, right? Is a function of theta? No, okay. What about Z? At Z, does VZ change? Pulling steadily? No, okay. So VZ is a function of R only. All right, let's work on the rest of the problem.
แล้วก็มีแนวเพราะว่าพอเรานึกแล้วแต่กับแนว
ได้ดูสมการมีคำถามไหม
ก็เหมือนข้อกำหนดเด็กข้อกำหนดเด็กที่มันเขียนข้อเนี้ยก็คือมันไม่มีเป็นเขียนมันมีหลากหลาย
มองให้เดียวเราได้ฉากนะคะตัวที่ได้มาได้แก้นะช่วยแก้ก็ได้ได้นะคะได้ตรงนี้
ในตอนที่
ไอ้รอบของมันสับอาเท่ากับอาสองอาเท่ากับอาสองอีกแล้วก็เพราะว่าฉันบอกไอ้การว่าเรื่องมันทำแต่ถ้าการการมันแบบแก้ยังไง
มันต้องเรียกว่ามีเท่ากับ
ข้อนี้ถือเป็นเพื่อความรู้ฉะนั้นเราจะแต่เป็นมีสูตรเวลาจะได้ดูเป็นภาพทุกทีถ้า R เท่ากับ R 1 velocity เป็นเท่าไหร่ที่ศูนย์ต้องเป็นใครกับ R หรือว่าเรื่องนี้เนี่ยของเราที่ตกเป็นได้เลย
โต
zero and air This one is zero.
Yeah. Probably more. No, ร้อยมันมีดิวอาร์คุณแล้วก็มีที่ตัวอันนี้ถูกแล้วก็ใหญ่สนุกมันไอปีว่าคืออะไร
Zoom อัตตาใครอยู่ในนี้ป่ะคะเป็นอัตตาอาลาคาน Are you here or in Zoom
Yes, dear professor,
Yes.
I'm here.
Are you in Thailand already
No, I am not in Thailand. I applied for the visa and it will take some time.
when are you coming here do you know the arrival date
Near to 20,
huh
near to 20 February.
14
20,
or 1
18
week
or
okay
20.
all right okay I'm just checking
Oh,
so I think you're the only one who haven't arrived yet so it's okay
yeah. I am the one because there was some problem in the visa, so I just
See.
apply again.
All right. Okay.
Okay.
Okay. How's everyone so far? So as I've walked around, you are still working on the Navier-Stokes equation, right? So do you need a few more minutes or you want to go through the solution now? You want the solution now, right? Okay. Does anyone, I'm not going to write the assumption for this problem anymore, okay? Does anyone applying Navier-Stokes equation for this problem? Does anyone applying the Navier-Stokes equation, which is this equation right here? Yes? Yes, right? Yeah, as far as I've walked around and take a look, I think most of you are applying this equation, okay? Which is true, which is applicable, okay? But let me show you this. What if I apply B5 equation, which is the equation of motion, by using in the form of the shear stress? Can I do that? Can I do that? Instead of Navier-Stokes equation, can I apply general equation of motion? Can I also use this equation? Yes, right? The answer is yes, because actually this is a general equation, all right, for equation of motion. And Navier-Stokes equation actually derived based on this equation, okay? So even if you don't apply Navier-Stokes equation, you can actually use equation of motion or B5 equation also, all right? So even if it's in terms of shear stress, but don't forget that we can transform shear stress in based on B1, equations in B1, right? Because at the end, all components of shear stress will be equal to, will be in the function of velocity anyway. Is that right? So at the end, the answer should supposed to be the same, okay, if you do it correctly. So in this one, I'm going to show you by using B5 equation, okay, and also Navier-Stokes equation to show you that either one, you will get the same solution, all right? So let me use B5 equation. So in this case, we are applying the cylindrical coordinates, okay? Let me ask you this. We have a total of 9 components of shear stress, right? Like I mentioned last time, like right here. Oh, sorry, it's a little bit delayed. 9 components right here. In this problem, what components of shear stress do we have? Tau RZ, tau ZR, tau R theta, which one? Tau ZR, RZ, right? Yeah, tau RZ, because we have a momentum in Z direction, transferring in R, okay? Because the wire is moving in Z direction and the momentum is transferring in R direction. So what we have is the tau RZ, okay? So from equation B1, again, we're going to use the bottom equation right here, okay? So we don't have VR, right? So I'm just going to neglect this term, all right? We only have this one. So what we have left is negative mu dVz by dr, all right? All right, let's take a look at equation B5 again. B5, all right. So I'm just going to neglect the R direction. This is R direction, right? Theta direction, and this is Z direction. I'm going to neglect R direction and theta direction because we don't have VR or V theta in this problem, okay? So let's focus on the last equations right here. Do we have dVz by dt? No, because steady state, okay? This one, VR 0, V theta 0. What about this term? Do we have this term? Do we have this term? No, okay? Because Vz is not a function of Z, all right? On the right-hand side, does pressure change in Z direction? Does pressure change in Z direction? So we slowly pull the wire, right, in the die. So in this case, we can take that pressure doesn't change in Z direction because it's moving so slowly. Okay, so in this case, this can be taken as 0. All right. Next one. Next one. Is this term 0? No, right? So we keep this one. Okay. I'm going to circle it. So these are all 0, right? Okay. What about the last term, rho gz? Do we have gravity? No, because if you take a look at the picture right here, our system is defined within this very, very narrow channel. Okay, so the effect of gravity can be neglected. Okay, so in this case, the GC can be taken as 0. Okay, so what we have left is only one term. All right, we only have one term. So let me write this. It will be equal to 1 over R Z divided by 6. All right. So just do one integration, okay? So one integration will be equal to C1 over R, okay? Again, this will be different approach to what you did because I start from general equation of motion, but you all started with the Navier-Stokes equation, right? So we're going to compare that we have the same solution, all right? Okay, so we have this equation right here. So we're going to substitute into this equation because it will be in the function of velocity. Okay, so substitute this term into this equation right here that we got from B1. Remember? Okay, B1 right here, Newton's law of viscosity. Okay, so that will be equal to so if I define C1 prime equal to minus C1 over mu, okay? Because I'm going to move mu to the other side, okay? So, all right, let's wait for just a second. Done? All right, so it will be dvz equal to c1 prime over r dr. So integrated, that will be c prime log r plus c2, okay? All right. We need two boundary conditions to solve for c1 prime and c2. Is that right? Okay, what would be the boundary condition? It will be something, the velocity at different r, right? So at r equal to r1 and r equal to r2, velocity vz. At r equal to r1, what would be the velocity? Oh, sorry. 0. R equal to r1, what would be the velocity? Everyone, we're almost done here. 0, r equal to r1, v 0, right? Because the wire is moving, right? So any fluid that is in contact with the wire needs to have the similar velocity, okay? All right, so the v equal to v naught. At r equal to r2, vc will be equal, in this case, it will be equal to 0 because the slot die is staying still, okay? So the velocity is 0. All right, so just solve it, okay? So I'm not going to detail in solving this equation, all right? I'm not going to spend time on this. I think you can work it on your own, all right? So I'm just going to give you the result, all right? Vz V0 equal to log R R2. All right, that is it for this problem. Please solve it on your own, all right? But what if we start with the Navier-Stokes equation? What will you get? It's supposed to be similar, all right? It's supposed to be similar. So please compare to what you did earlier to the solution that I got right here, okay? Please finish the rest of what you did and then compare the results. It's supposed to be the same, okay? So again, even if we are familiar with using the Navier-Stokes equation B6, okay? But it doesn't mean that you cannot apply B5 equations. You can do too, because basically B5 and B6 equations are all the same, okay? Except that Navier-Stokes equation can be used for incompressible fluid and Newtonian fluid only, all right? Any questions about this? All right, last but not least, what would be the momentum flux? What would be the momentum flux in this case? Yeah, ค่ะ B1 อะไรนะ B1 เดี๋ยวนะไล่ไปก่อน B1 โอเคค่ะ yes yes VZ not theta yeah ตรงนี้ใช่ไหมโอเค since you are still confused I mean still wondering if the results are going to be the same right let's work on the Navier-Stokes equation altogether too so let's start with B6 okay B6 okay this one cylindrical coordinates all right again I'm not going to ignore the r and theta direction I'm going to just focus on the z direction so in z direction this will be 0, right? Steady state, this VR with theta is equal to 0. This is also 0, 0, 0, 0, 0. Okay. What you have left is just only this equation. Is that right? Okay. And then, let me write this. Navier-Stokes. Okay. You get dr dvz by dr equal to 0. Is that right? Okay. All right. So do the integration. So you will get dvz by dr c1. Okay. มันรีเลทกับ B1 ยังไง อันนี้เหรอ อันนี้ อันไหนนะหน้านี้เหรออันไหนนะหน้านี้หมดแล้วอ่ะ Okay. Sorry. This one right here, right? อันนี้เหรอ อันถัดมาที่เท่ากับอันนี้ This is the equation of motion. This is the equation of motion. Okay. So it's like if you apply the equation of motion, which is in this page, right? It's like a two-step because you start from shear stress first, and then you transform it in as a function of velocity. Okay. So it will be in this one. But if Yes. But if you start from Navier-Stokes equation, it will just like a one step because you don't need to transform from shear stress into velocity. Okay. The reason why I'm showing you this approach is that I don't want you to stick with the Navier-Stokes equation only. I want you to be able to apply B5 equation too, because B5 equation, even if it's in the form of shear stress, you can transform it into in the form of velocity as well by substituting the Newton's law of viscosity, which is B1. Okay, so it's more like a two-step process. Yeah, it will be longer, but at the end, the solution will be the same. Yeah, good question. Thank you for bringing it up. Because sometimes you might see a system that is dealing with compressible fluid. That means that you cannot use Navier-Stokes equation, right? So that's why I want you to be able to apply B5 equation as well. All right. So I'm not going to go through this then. All right. All right. What would be the momentum flux? Momentum flux. Momentum flux will be RZ, right? RZ. Can you find shear stress RZ at where R equal to R1 for me? Shear stress RZ, tau RZ where R equal to R1. What would it be? So if they ask for further questions of the momentum flux, what would it be? What would be tau RZ? You previously got this term already, right? Tau RZ, right here. Is that right? So you already know C1 over R, right? So just substitute C1 over R, and that will be the answer for the tau RZ. Is that right? Because earlier I didn't give you the results for, give the solution of the C1, what the C1 and C1 prime is, right? And C2. So yeah. So it will be C1 over R. C1 over R. Please work on this by yourself, all right? C1 over R1, because we define where R equal to R1, okay? So that will be equal to mu V0 log R1 over R2, 1 over R1, okay? เห็นไหมซูมให้นิดนึง อันนี้เขียนย่อๆให้แต่คำตอบไปนะคะ ไปหาเอาเองนะก่อนที่จะได้ตรงนี้มันต้องหา C1 C1 พราม C2 มาให้ได้ก่อนโอเคปะข้อนี้อาจารย์ไม่ทำละเอียดแล้วนะมันเป็นแมททั่วไปอะค่ะเพราะข้อที่แล้วทำละเอียดมาก all right any questions about this all right last but not least what would be the force needed to pull the wire same questions just like the previous exercise, right? We asked for the velocity profile, momentum flux, and last one is the force exerted on the fluid. This one is the same. What would be the force exerted on the wire? Force. What would be the force needed to pull the wire? Same approach just like the previous exercise, right? So it will be equal to tau RZ times area, right? So what is the area? Force needed to pull the wire. So it will be the area would be 2 pi R1 or R2. R1 or R2? R1, right? L. Okay. So I'll just give you the answer again. 2 pi mu V L log R1 R2. Okay. Any questions? 2, yes, 2 pi. Any questions about these 2 exercises that we worked on today? You lost it already. After the break, I feel like you guys like, I don't take it anymore. Yes. One of your friends is asking about midterm exam already. Yeah, if it will be open book or closed book. You want it open or closed? Oh, of course it will be open. All right. Any questions? Any other questions? If not, then see you guys next week. Next week, we're going to go to the last topic, which is the energy transport. All right. We'll derive the last equation of the appendix B right here. Okay. All right. Have a good day, guys. Don't forget about homework too. I'm going to post it on my course view today. All right. Bye.